Assalamualaikum and salam sejahtera. Welcome to my presentation for the first UMS Colloquium on Fundamental Research and Application UMSCoFA2020. I'm Muhammad Azrul Abdul Rajak, would like to present a paper entitled Morphology of Lightweight Metakaolin-based Geopolymer Polystyrene Composite PPST at Early Ages. So this is my outline of my presentation, includes introduction, objectives, experimental results and discussion, last but not least, conclusions. First, we look into the introduction. Geopolymer. Geopolymer is an aluminosilicate-based polymer where it contains amorphous form and three-dimensional structures composed of SiO4 and Al4 bonds formed in tetrahedral structure with sharing of oxygen atom that give various terminology. If you can see from the diagram of the Davidovich model of geopolymer structure, there are various terminology of silicon and aluminium, where the silicon and aluminium were bonded with the oxygen atom in tetrahedral structure. Recently, geopolymer is being used as a cement replacement because geopolymer concrete give a high compressive strength, high fire resistance, and high chemical resistance. Geopolymer can be formed when the aluminosilicate precursor, for example metakaolin, fly ash, and GGBSF, is added with the alkaline activated solution and aggregates. Then this mixture will geopolymerize to form the geopolymer concrete. Next, we move into the metakaolin. Metakaolin has a formation of amorphous phases that is produced through a calcination or thermal treatment process of high purity kaolinite at high temperatures ranging from 700 to 850 degrees Celsius. This material or metakaolin is a good raw material for geopolymer concrete because first, this material is a highly available material, and then instead of giving a structure of geopolymer, metakaolin also can act as a filler. Metakaolin can produce a high strength of concrete and also high durability of concrete to the chemical resistance. Next, about the polystyrene beads. This material is a light thermoplastic material having a low density, high durability, antifungal, low thermal conductor, and stable chemical properties such as anti-aging and anti-corrosion. This material can provide a high capacity in development of a lightweight concrete, where the lightweight concrete possesses a low density and frequently used in multi-story buildings, wide coastal structure, and long bridges. From the previous study, it shows that metakaolin can act as an alternative cement replacement because it can produce high strength and high durability of geopolymer concrete. Meanwhile, polystyrene beads can enhance the properties of lightweight concrete geopolymer. The combination of metakaolin and polystyrene beads can produce the lightweight metakaolin-based geopolymer. However, the numbers of the reports on the microstructure studies for this material is not very significant because most of the studies focus on the mechanical and durability properties of this concrete. Therefore, it brings to my aims and the objective of my research. The aims of my research is to form the lightweight metakaolin-based geopolymer incorporating polystyrene beads. Meanwhile, the objective of my present study is to investigate the morphology of lightweight metakaolin-based geopolymers incorporating polystyrene beads as a lightweight agents at early ages. The significance of my present study is to discuss the contribution of polystyrene beads as lightweight agent at early ages based on the microstructure study of metakaolin-based geopolymer. Next, we go to the experimental of the study. The present study involves three stages, includes the preparation of metakaolin, the preparation of lightweight geopolymer metakaolin paste, and the last but not least, the morphology analysis of lightweight geopolymer metakaolin base. First, we look into the preparation of the metakaolin. The metakaolin are prepared from the calcination process of kaolin through thermal treatment at 800 degrees Celsius with a heating rate of 5 degrees Celsius per minute for 2 hours. Then, the mineralogy analysis and FTIR analysis of metakaolin are conducted. In the preparation of lightweight geopolymer metakaolin-based paste, 10 molar of sodium hydroxide solution were used as an alkaline solution. For the mixture, alkaline to metakaolin ratio of 0.7 was used. Then, the mixture be added with the 0.3% of polystyrene bits as a lightweight agent. For the process of the preparation, the mixture are mixed until obtain the homogeneous solution. Then the mixture will cast in the cubic mold. After cured at 60 degrees for 24 hours, the cubic were removed and the cubic was stored at room temperature until 14 days of curing age. Next, for the morphology analysis of lightweight geopolymer metakaolin-based, the morphology of geopolymer were analyzed using Hitachi S3400 and silicon emission microscope. In this analysis, a small geopolymer paste fragments were captured using SEM and operated at 15 kV. Now, we move to the important part of my presentations today, which are results and discussions. First, we look into the mineralogical and FTIR analysis of metakaolin. First, we go to the mineralogical analysis. Figure 1 shows the de facto gram of A. kaolin and B. metakaolin that obtained at 800 degrees Celsius. Based on the de facto gram, in figure 1a, the presence of kaolinite can be observed based on the intensity peaks at 2 theta, which are at 12.26 and 24.8. Meanwhile, the intensity peak at 2 theta, 26.57, this one, indicate the existence of quartz. In figure 1b, the de facto gram of metakaolin shows the intensity peaks of quartz at 2 theta, 26.57 and 31.3, which indicate the quartz is a major crystalline phase in this material. In addition, the de facto gram of metakaolin depicts the reduction of kaolinite peaks presence compared to the peak of kaolinite in the de facto gram of kaolin in figure 1a. It shows that the thermal treatment of kaolin at 800 degrees Celsius activates the breakdown process of the crystal lattice structure through the dehydrogenation of the water molecule that exists in the kaolin. As a result, it forms an amorphous structure of metakaolin that is rich with an active silica and alumina content. Next, we look into the FTIR analysis. Figure 2 show the FTIR spectrum for A. kaolin and B. metakaolin. In figure 2a, the appearance of strong band ranges from 36 at 3.05 per centimeter to 3619.94 per centimeter. This one indicates the oxygen-hydrogen bond symmetric stretching vibration as it proves the presence of water molecule. A sharp peak at 992.07 per centimeter correspond to the silicon-oxygen bond asymmetric stretching vibration resulting from the silicon-oxygen, aluminum or silicon bond. Meanwhile, the band peak at 797.39 per centimeter, 747.82 per centimeter, and the strong band at 520.31 per centimeter correspond to the bending vibration of silicon-oxygen aluminum bond. In addition, the strong peak at 937, the 937.01 per centimeter indicates the stretching vibration of aluminum-oxygen hydrogen bonding. Meanwhile, in figure 2b, the appearance bands at 1,02713 per centimeter imply to the silicon oxide silicon bond or silicon oxide aluminum bond asymmetry stretching vibration. The appearance of these bands is due to the transformations of kaolin to metakaolin forms and alternating chain between SiO4 and Al4 by sharing an oxygen atom in a tetrahedral coordination. Next, the band at 570.4 per centimeter and 538.97 per centimeter correspond to the bending vibration of silicon-oxygen aluminum bond, and the band at 465.23 per centimeter indicate the presence of bending vibrations of silicon-oxygen silicon bond. Meanwhile, it observed that the peak from the stretching vibration of aluminum oxygen hydrogen at 934.1 per centimeter, similar with the FTIR of kaolin, did not appear in the spectra of metakaolin. It is suggested that the loss of this peak is attributed to the transformation of kaolin to metakaolin through the calcination process. Next, we move to the results and the discussion of the morphology characteristic of lightweight metakaolin-based geopolymer polystyrene paste. Figure 3 shows the SEM micrographs of lightweight geopolymer metakaolin-based paste at 14 days curing ages. The numbers that you can see on the micrographs shows the important indication. Number 1 indicate polystyrene form. Number 2 geopolymer binders. Number 3 indicates the unreacted metakaolin, and the number 4 indicates the presence of porous gel. According to the figure 3A until 3D, it is observed that the lightweight geopolymer paste is filled with homogeneous matrix of unreacted metakaolin, polystyrene forms, and polymerization geopolymer products. Meanwhile, it can be seen that the paste of the lightweight geopolymer on this early age does not give a dense and compact microstructure. The homogeneous geopolymer binder is detected in all micrographs, and it is a main product of the geopolymerization reaction. However, the agglomerate particles of unreacted metakaolin appeared in the geopolymer paste, and it can be observed in figure 3A, this one, in figure 3A, this one, and figure 3B, number 3. The polystyrene bits also were detected in the paste as it coated with the geopolymer matrix, and some of polystyrene bits are observed with shrink and melt structure. The black hole, as it can be detected as the porous gel, number 4, okay, also appeared on the microstructure of the geopolymer matrix. The observations from the SEM micrograph brings to the discussion. First, the dissolution of metakaolin in an alkaline activator produces a homogeneous matrix through the polymerization of aluminosilicate material. In addition, the geopolymerization produces an agent binding in the paste, which contributes to the main mechanical strength and durability in the geopolymer. It is suggested that the appearance of agglomerate particles of metakaolin is due to the fact that in the early age, the metakaolin are likely not completely gone through the geopolymerization process. Then it brings to the explanation of, first, the formation of porous gel, which represent the capillary gels, and also it is predicted that these porous gels will reduce at a later age as the geopolymerization of metakaolin continuously occur in the matrix. The second, the microstructure of lightweight geopolymer during early age does not provide a dense and compact microstructure. From the observation, it also confirmed that the polystyrene bits are blend well in the geopolymer matrix. This is an important factor that needs to be considered in the process of integrating polystyrene bits as a lightweight agent so that it can reduce the density of the products. However, it is suggested that the high temperature at 60 degrees Celsius during the curing process give a possible structure damage to the polystyrene bits, as it is confirmed in the results. Thus, this discussion brings to the conclusion of the present study. First, it can be concluded that the pairs of the lightweight metakaolin-based geopolymer give a less dense and compact microstructure in the early edges, which are contributed by the unresponsive metakaolin in the geopolymerization process. However, it is suggested that the microstructure will improve as the geopolymerization process continuously occurs in the geopolymer matrix. It also can be concluded that the results from the morphology analysis confirm that the polystyrene beads are integrated in the geopolymer matrices, as the presence of this material will provide the lightweight products and increase the density of the products. For the acknowledgement, the authors gratefully acknowledge the funding supported by University Malaysia Sabah under Acculturation Scheme Grant SGA 0082-2019. The authors also thank the staff of the Preparatory Center for Science and Technology and the Faculty of Science and Natural Resource University Malaysia Sabah. These are some references that included in this presentation. That's all from me. Thank you for your attention.